Hello everyone. Today we are going to talk about work and energy. So let's start. There are many ways to show you where it comes from. I'll show you this way. So our topic is work and energy. Okay, let's take this equation from kinematics. If you remember, it was this one. 2a delta x equals to v final squared minus v0 squared. Okay, let's do something with this equation. Let's divide it by 2 and multiply it by m. Just mathematical thing we can do. Okay, if I divide it by 2, the 2 goes, multiply by m is ma delta x equals to m vt squared divided by 2 minus m v0 squared divided by 2. Now, what is ma? According to the second law of Newton, ma is the net force, the total force that is applied on the object. So instead of it, I can write F total, or just F, multiplied by delta x is that minus that. Okay, I got this equation. Now, just a minute. Okay, now let's define some things. Let's call this work with the letter W, which is F multiplied by delta x. And when I write F, it means the total force applied on the object, and this force must be in line with the acceleration, because it came from ma. Remember ma from the acceleration, a that is the acceleration. I'll talk about it later, just write it down first. W is F multiplied by delta x, and let's define something this mv squared over 2. Let's call it kinetic energy, the kinetic energy of an object. We'll symbolize it like that, Ke, kinetic energy. According to these definitions, I can say that the work applied on an object equals to the kinetic energy at the end minus the kinetic energy at the beginning. Vt is V final is the final velocity, V0 is the initial velocity. So the work applied on an object is the final kinetic energy it has minus the initial kinetic energy it has. Let's talk about this a little more. Now, suppose I have an object and I apply force on it, but the force is with an angle like that, F, and this object is moving, accelerating in this way. So the acceleration is here, and this is delta x. According to this, the work applied on an object must be the force in the direction of the acceleration. If I divide this force into its components, this will be F cosine alpha, this will be F sine alpha. So when I write W equals to F delta x, I mean F cosine alpha multiplied by delta x. Or usually you will see it as F delta x multiplied by cosine alpha. And the alpha will be always the angle between the delta x and the force. There are a few things that are we can conclude from this. There are three important things we will be using a lot. So let's talk about them. We'll be using a lot a force which is parallel to the delta x, like that. This is first example. Suppose I have a force here, and it mass accelerates in this direction. So the work will be F multiplied by delta X, and that's it. Why I don't need the cosine alpha? Because alpha here is 0, and if you do cosine 0, you'll get 1. So it's multiplied by 1. We can just write it like that. Second example is, again, the mass is going this way, but the force is in this direction. Usually it's friction force. We'll talk about it later today. So probably this mass is going to accelerate in this position, in this way. It means it's going to slow down, negative acceleration. The work will be of this force minus F multiplied by delta X. Why the minus? Because alpha is, the delta X is this way, and alpha is 180 degrees. So if you put cosine 180, you will get minus 1. This is where the minus comes from. Okay, 3. The third thing I want to show you. Again, if the mass is moving this way, and the force is this way, suppose it's not strong enough to lift it from the ground, just make it a little lighter. Press lighter on the ground. This force, the W of this force will be 0. Why? Because the angle is 90 degrees, alpha is 90 degrees, and if you do cosine 90, you'll get 0. So this force doesn't do any work on the mass. It doesn't give, and we'll talk about it later. Okay, so the work here is 0. Okay, let's practice a little bit what is written here, and then we'll talk about it even more. Okay, so I'm wiping it off. Okay, suppose I have a tower, 80 meters height, and I drop a ball from a velocity 0. And I want to know what the velocity will be when it reaches the ground. V final, or Vt. How will I find it? First of all, we can calculate it in kinematics. We know how to do it. We saw it earlier. We can write V0, acceleration, delta X, everything, and find the V final. Another way to approach this problem is to use this equation. What forces are applied on this object? Obviously the mg, and that's it. Now look, if I want to use this equation, I do it this way. The force is this direction, and the mass moves exactly in the same direction. So if the force is with the direction, the work which is done on this object by this force is mg, which is the force, multiplied by the delta x, which is the 80. And according to this equation, it must be equal to the mass multiplied by the V final squared over 2 minus the mass V initial squared over 2. I can divide it by m, so 10 multiplied by 80 will be V final divided by 2 minus 0, because V initial here is 0. So I can find the V final here. V final will be 840. Okay, this is one example to show you how this equation works. Another example. Let's say I have a mass here, and I pull it, doesn't matter, with a force of 10 newtons in a direction of, let's say, 20 meters. And let's say the initial velocity of this mass is 10 meters per second. And I want to know when it reaches here, what will be the final velocity. Again, I can do it with our knowledge in kinematics and forces. I can find the acceleration, and when I find the acceleration, I can write, I have the initial velocity, I have the acceleration, I have the distance. I can use the kinematic equations and find the velocity here. I want to use this. Again, how do I do it? Let's see what forces are applied on this object. Obviously it's an mg. Let's say m is 2 kilograms, okay? Normal force, obviously, and this force. There are 3 forces applied on this mass. According to this equation, I need to write this equation, talk about each force. These 2 forces are perpendicular to the delta x. They are 90 degrees, so the work will be 0, so they don't count. Only this force counts, because when we use this equation, we want only the force with the direction of the delta x, of the displacement. So according to this equation, I can write F multiplied by delta x will be m v finals over 2 minus m v initial over 2. So 10 multiplied by 20 will be 2. Okay, minus 2 multiplied by 10 squared over 2. And from here I can find the v final. 2 is that, I take it like that. 200 minus v final squared equals to v final squared minus 100. So v final will be the square root of 300. Okay, another example. Third example. Let's say I have, again, a tower. I have a ball here, and I lift the ball up. Let's say the mass is 2 kilograms again, and I use a force of, let's say, 50 newtons, and it started with the velocity 0, and I lift it with a force of 50 newtons up here. Let's say this height is 40 meters. I want to know the velocity here. Again, what can I say? I can do it with kinematics and forces like we did it earlier. I can find the acceleration. After that I can do kinematics and find the velocity. If I want to use this example, what do I do? Again, I find the forces applied on this object. The forces will be 50 newtons obviously, and the mg, which is 20 newtons, mg. Normal force will not be applied here, because once the 50 overcomes the 20, it will lift off, and the normal will be 0. So let's see what I can write. I can write that this force is with the way, with the delta x, with the direction. This force is against the direction. So I can do it with the total force, I can do it separately, it doesn't matter, you will see it now. So I write 50 multiplied by 40, which is the force multiplied by the direction, minus the 20 multiplied by 40. What I wrote here really is like 30 multiplied by 40, which means the net force, the total force, which is 30 multiplied by 40, and it's plus because it's with the direction of the acceleration, with the direction of the displacement, must be equal to m multiplied by v final squared over 2 minus m v0 squared over 2. So I'll get 1200 equals to, mass I say 2 kilograms, so they go, v final squared minus, this is 0 because v initial is 0. So v final will be square root of that. Okay, it's enough examples to illustrate what this means. Now, let's talk about this equation a little more. If I want to talk about, with terms of energy, I want to show you this equation in this way first. I'm moving the mv0 squared to this side of the equation, plus f delta x equal to m v final squared over 2. What is written here is this. The kinetic energy of the object plus the work done by the total force all the forces that applied on this mass, so the kinetic energy plus all the work that the forces applied on this mass must be equal to the kinetic energy at the end. Begin, end, and this is the work of all the forces, all the external forces applied on the mass. So we call it conservation of energy. Why? Because if I have an energy, kinetic energy of a mass, and I apply work on it, it will add to this kinetic energy and it will give us a new kinetic energy. If I don't apply any work on the mass, it means that the kinetic energy remains the same. Like the first law of Newton. If I don't apply any work, means that there are no forces on this in the displacement, in the direction of the displacement, which means the kinetic energy doesn't change or the velocity doesn't change, so it will stay in the same velocity. Okay, the energy, kinetic energy, is measured by units called joules. We write with the letter J, joules. The work is defined by joules, kinetic energy is also by joules. So when we say kinetic energy like 40, 50 joules, 60 joules, etc. Now, let's go back to our first example. Our first example was that we had a tower. I'm writing H now, no numbers, and I have a ball here. And this ball, and let's say the initial velocity is 0, is falling, and I want to know the final velocity. Let's use this equation again, okay? I want to show you one more thing. Forces applied on this object is only the mg, and it's with the direction of the displacement. The displacement is this way, and the force is also this way. So, what can I write according to this equation? The initial kinetic energy of this mass, which is mv0 squared over 2, plus all the work done on this object. The work done on this object is only by this force. And this force will be mg multiplied by the direction, which is h, by the displacement. And it's plus because mg is with the direction. This will be equal to the kinetic energy in the end, which is m v final squared over 2. And I can solve it and find whatever I like. The v final, obviously. If I have this and that, I can find that. Now I want to define one more sort of energy. This was the work done by the mg force. This mgh we can define as potential energy of an object. Let's write it. mgh equals the potential energy of the object. We write it really gravitational potential energy, but we'll just write potential energy. And if we treat it as so, as potential energy, we can write now this equation, we can understand it in another way. We can understand it like this. The kinetic energy of the object, which was 0 at the beginning, plus the potential energy, gravitational potential energy of the object in the beginning, which is due to its height. It has a certain height from the surface. So because it has height, it has a potential energy. So these two energies are equal to the final energy it has, which is only velocity. So let's define now the conservation of energy in this way. The total energy at the beginning plus all the external forces applied on the object equals to the total energy at the end. This is begin, this is end, And when I'm writing total energy, I'm referring to potential energy and kinetic energy. And also here, potential energy and kinetic energy. And when I write W external, I'm referring to all the forces applied on an object without the mg. Without the mg. Why without the mg? Because the mg is already here in the potential energy. So when we write potential energy, it means that I already used it, so I don't use it again. This is how we are going to treat all the problems now we are going to deal with. This is the law that defines the conservation of energy. It means that if an object has initial energy due to its velocity or due to its height, and some other forces are applied on this object and make work on it, do work on it, so the initial energy plus the energy that the forces gave or took from this mass must be equal to the final energy that this mass has, which will be also potential energy, referring to its height, and kinetic energy, referring to its velocity. Now we're going to do many examples to show you how to deal with this equation. So I'm wiping it off, and I'm writing in the corner just that. Kinetic energy is mv0/2, potential energy is mgh, and W is F mod dot delta X, and initial energy plus W equals to, let's say, initial, final, external, without mg. Okay, so many examples, and I hope you will understand how to deal with problems after that. So now we really start our lesson. Okay, first, okay, let's do this one again. I have a tower, let's say 100 meters, and I have a ball. I drop it in a velocity of 20 meters per second, and I want to know what the velocity will be when it reaches the ground. V final, what is it? Okay, look how the problems are very short, it's very easy, just you need to practice how to talk to yourself when you solve these kind of problems. First of all, you need to know which forces are applied on this mass. In this case, only the mg. Okay, so let's use this equation and find the final velocity. Let's talk first. In the beginning, it has kinetic energy? Yes, it has, because it has a velocity. So mv0/2, this is the kinetic energy it has in the beginning. Plus, it has height? Yes, it has height. It has 100 meters. So mgh, this is the potential energy. So in the beginning, this is E initial. In the beginning, it has both this and that. Plus, let's talk now about the W, the work done on this mass. What forces applied on this mass? Only the mg, but we said without the mg. So if we neglect the mg, there are no forces applied on this mass, so the work will be 0, which means that there are no work done on this mass. Which also means that the initial energy of this mass must be equal to the final energy of this mass. When this mass reaches the ground, 1 millimeter from the ground, it has velocity, which means it has kinetic energy, which is mv²/2. Plus, let's say, does it have height here? 1 millimeter, it counts as no height. So there is no height here, so it's 0 potential energy. So this is the E final, and this is the work. This is how I use this equation. The initial energy plus the external force done on this mass without mg must be equal to the final energy, and here it only has velocity, which means kinetic energy. And now just put numbers in it. First of all, you can wipe off the m. V0 is 20 squared over 2 plus 10 multiplied by 100 must be equal to V final squared over 2. Okay, you go to the calculator and find it. 20 squared divided by 2 plus 1000 multiplied by 2, so it's 2400 squared VT. Okay, one more. 2. Let's say I have this tower again, h 100 meters. I throw the ball again at V0 20 meters per second downwards, but I want to know what the velocity will be here. Let's say this height is 30 meters from the ground. What the V final will be here. Okay, there are also many ways to show it. Let's talk about it. First of all, I'm going to use this equation again. Okay, let's start by saying that the force applied on this object is only the mg, and we said mg we are not counting it as external work. So I want to know what the initial energy this ball has. It has velocity and it has height. But when I say height, I need to define height from where? From here, from here, from here. First of all, it doesn't really matter. But when you talk about height, you must have a reference point. Let's say, I want to define that this is the reference point when I calculate the height, okay? This is the reference point. Okay, just a minute. Reference point, okay, it's enough reference. Okay, when I measure heights, I measure it from here. So, let's talk again. At the beginning, I have kinetic energy, which is mv squared over 0 squared over 2, plus I have potential energy, because I have height, which is mg h, and the h I use is 100, because the height in the beginning is 100. Work is 0, because this is the only force I have here, and in the end, when it reaches here, it has also kinetic energy. I want to find it, plus height, and the height is 30 meters, mg multiplied by 30. So, again, at the beginning it has kinetic energy and potential energy, and in the end it also has kinetic energy and potential energy. Now look, something very nice. If I take this mg30 to this place, I'll get mv squared over 2 plus mg100 minus mg300, each mg multiplied by 70 equals to mg vt squared over 2. What is written here really means that if I were to use this line as a reference point, not this, reference, for the height, for the potential energy, I will automatically get this equation. Look, at the beginning it has height and speed, height and velocity, and the height will be 70, and in the end it only has velocity because it's on the reference point, so it means that there is no height. So it just illustrates to us that it really doesn't matter from where you calculate or measure your height. So every problem you have, just define a reference point, and this reference point, from there you're going to measure your heights. Okay, let's solve it. It goes, V0 is 20 squared over 2 plus 10 multiplied by 70 equals to V final squared over 2. So it's 400 divided by 2, which is 200, plus 700, which is 900, multiplied by 2 is 800, square root, okay. More, a lot more. Okay, this is another problem. I have a ball here, I pull it up with a force of 60 newtons, and the mass here are 2 kilograms, and initial velocity is 0, and it will reach here. I want to know what velocity will it gain, and the height, let's say, is 50 meters. Okay, I'll use this pen. Okay, so first of all, I want to know the forces applied on this object. 60 and mg, which is 20 mg. Okay, let's talk again in this language: initial energy, final energy, and external work. The initial energy is nothing kinetic, so it's nothing kinetic, 0 kinetic, plus 0 potential energy because it has no height. Let's say this is our reference point. So no velocity, no height, no initial energy. Okay, let's talk about the work. There are 2 forces applied on this object, 60 and 20. Now this we don't count because we said every force without the mg. mg is already applied, is already used when we talk about potential energy. So we don't use it again. So this is the only external force applied on the object. And the force is with the direction of the movement, with the displacement. So we write 60 multiplied by 50, which is the work done by this force. And the final energy this mass has, it has obviously velocity, kinetic energy, plus it gained height. Which height? 50 meters, because this is the reference point and it's 50 meters above it. So it's mg multiplied by 50. Look again. The initial energy, this is the final energy, the initial energy that this mass has, plus the energy, the force, the external force gave it, the initial energy was 0, the external force gave it 60 multiplied by 50 joules of work, and this is going to be the final energy of this mass, which is combined from kinetic energy and potential energy. Let's solve it. This is 3000 equals to m is 2, so this goes v final squared plus 2 multiplied by g, 2 multiplied by 10 multiplied by 50. So v final will be what did I write? Okay, so 3000 minus 2 multiplied by 10 multiplied by 50. Square root of 2000. This is the velocity there. Okay, more. Okay, this was 3, I think. 4. Okay. Okay, I have a mass with a velocity of, let's say, 60 meters per second, moving this way. And I have a force, let's say, friction force, mu kinetic is 0.2. And this mass is moving this way, and eventually it stops. V final is 0. Delta x. And I want to know what's the displacement until it stops. Okay, again, I have mass. I don't know the mass, it doesn't matter. I have a mass with a certain velocity, with initial velocity of 60. There is friction here, so the friction obviously is going to slow it down until it stops. And I want to know what was the way, what was the distance, the displacement until the mass stopped. Again, let's use this equation. First of all, the forces applied at mg, the normal force, and the friction force, obviously this direction because the movement is here. I remind you, F kinetic is mu kinetic multiplied by the normal force, which is mu kinetic multiplied by mg in this case. Remind you. Okay, so let's use this equation. What's the initial energy of this mass? The initial energy is kinetic energy, obviously. No potential energy because obviously this is our reference point and there is no height here. So potential energy is not really, doesn't really talk to us here in this kind of exercise. Now so this is only the initial energy. Now let's talk about the force applied on the work applied by the forces on this mass. There are three forces here. The normal force, the mg force and the Fk. Both normal and mg we always neglect it, but here we neglect it from two reasons. First of all, we neglect it because it already is used in the potential energy, but it is also perpendicular to the delta x, and when the force is perpendicular 90 degrees to the way, to the distance, it doesn't do any work. The normal force exactly the same, it's perpendicular to delta x, so it doesn't do any work. So this force doesn't give or take energy. This force doesn't give or take energy here also. This force is against the displacement, so it takes energy from the mass, and so it's minus F kinetic multiplied by the delta x. This is the only work, external work done on this mass. It's minus because it's against the delta x. Equals to, at the end, there is no kinetic energy, obviously no potential energy because there's no height, so this is the equation. Which means that mv0 squared over 2 minus, instead of F kinetic I can write mu kinetic mg equals to 0. What does it really mean? It means that all the kinetic energy of the mass, who took this kinetic energy? The friction took it, the work of the friction force. It means that all this velocity, which means all this kinetic energy, was interpreted into another energy, the energy that the kinetic force took. It means, in other words, the kinetic force usually is a friction force. It is rubbed with the surface, it makes heat. So all the kinetic energy is turned into heat energy, probably, or something like that. And from this equation we can find forgot the delta x. The delta x. Okay, so m and m goes. V0 is 60 squared over 2 minus mu kinetic is 0.2 multiplied by 10 multiplied by delta x equal to 0. So delta x will be here 60 squared over 2 divided by 0.2 and also divided by 10. Ooh, 900 meters. Okay. More. Okay, let's say I have this. We are talking 5. Okay, alpha here is 30 degrees. I have a mass here. Let's say this is h equals to 10 meters, okay? And the velocity, initial velocity is 0, and I have friction here, mu kinetic is 0.2. I want to know this mass, let's say it goes down, I want to find the velocity it has when it reaches the ground. Okay, let's apply force on this object. mg, normal force. These are the two forces applied on this object. If we were to solve this problem with kinematics and forces, we were to divide the force. I said friction force also, sorry. So friction force also here, friction force. We would find the acceleration and then find after the acceleration we can find with kinematic equations the final velocity. Here, what we are going to do, okay, let's just divide I remind you, this is alpha, this is mg cosine alpha, this is mg sine alpha. Okay. I want to solve it with energy. So how do I talk to myself? First of all, let's say this is our reference for the height. When this mass at the beginning, it has no kinetic energy because there's no velocity, so zero kinetic energy, but it has height. How much height? 10 meters. So mg multiplied by 10, this is the initial energy of this mass. Okay, let's talk about all the forces applied on this mass. There's the mg force. We separated, but still it was mg at the beginning. The mg, we neglect it, we don't really use it, so forget the mg. The normal force will not do work. Why? Because the displacement is this direction and the normal force is perpendicular to it. So when a force is perpendicular to the surface, there is no work done by it. So the normal force is not doing any work. mg force, we don't use it because it's already used in the mgh. Only the friction force is what is interesting here, and it's against the displacement, so it's minus F kinetic multiplied by delta x. Delta x is this. When this mass is going to reach the ground, obviously it's going to have a velocity. I want to know the velocity, so it will be mv squared over 2. No potential energy in the end because there is no height. So again, look at the equation. The initial energy is only potential here because there is no velocity, no kinetic in the beginning. The external force or the external work done by the forces is only due to the friction force. And the final energy is only due to the velocity because there is no height. Okay, let's solve it. If this is 10, this is delta x. Delta x will be, with a little trigonometry, we know if this is h, this is delta x, sine 30 equals to h over delta x. So delta x will be h over sine 30. So delta x will be 10 divided by sine 30, which is 20 meters. So delta x is 20 meters. Okay, so m multiplied by g, which is 10, multiplied by h, which is also 10, minus F kinetic it's mu kinetic, multiplied by the normal force. The normal force is mg cosine alpha, multiplied by delta x, which is 20. This is F kinetic, this is delta x, must be equal to mv final squared over 2. So this is our equation. The initial energy, potential, minus the work done by the friction, only the friction, must be equal to the kinetic energy at the end. Let's solve it. M goes. So 100 minus 0.2 multiplied by 10 multiplied by cosine of 30 multiplied by 20 equal to b final squared over 2. So b final will be, I'm going to use my calculator, 100 minus 0.2 multiplied by 10 multiplied by cosine 30 multiplied by 20, it's something, multiplied by 2, square root 11.433. And if I have a mistake, it really doesn't matter. It matters that you understand how to approach these kind of problems. Okay. 6. Okay, let's do a more complicated thing. Let's do that. Okay, let's say I have a mass here, 2 kilograms, and I apply 2 forces on it. External force 20 newtons, and also it has friction force. Mu kinetic is 0.1. And let's say the velocity, initial velocity here is 10 meters per second. And this mass goes here. I want to find the velocity here. Okay. Okay, again. Initial velocity is 10. I use 2 forces on it. External force, which I pull it, and also friction force, which is, let's say the mu kinetic here is also 0.1. I want to know what will be the final velocity here. Again, let's write all the forces on this mass. 20 newtons, normal force, this is the mg of course, external force this one, and the friction force here. Okay. Potential energy is not relevant here because there's no height here, so let's forget about it. Only kinetic energy. At the beginning it has kinetic energy. Okay, let's talk about all the work done by the forces applied on this object. There are 4 forces here. 1, 2, 3, 4. mg we neglect it from 2 reasons. Why? First, it's already taken in the, we said don't use it because it's already here, so we don't use it. Second thing, it's perpendicular to the direction of the movement, so it's 90 degrees, it doesn't do any work. Normal force, exactly the same. It doesn't do any work because it's 90 degrees to the direction. There are 2 other forces I must use. This force is with the line of movement, with the line of displacement. So it will be 20, let's say the direction here is 10 meters, okay? Multiply by 10. This force is against the line of movement, so it will be minus F kinetic multiplied by 10. So this force gives us energy, this force takes energy from the mass. And when it reaches here, it only has kinetic energy. Again, the initial kinetic energy, because there's no potential here, plus the work done by the external forces, which are this force and this force, must be equal to the kinetic energy at the end. Okay? So 2 multiplied by V0 is 10 squared over 2, plus 20 multiplied by 10, minus F kinetic is mu kinetic multiplied by the normal, and the normal is mg. Multiplied by 10 equals to 2 multiplied by that over that. So it's 100 plus 200 minus mu kinetic is 0.1. This is 2, this is 10, this is 10 equals to V final squared. So V final will be 100 plus 200